So this is another problem out of John R. Taylor. It's the second one, very similar. Basically the same idea as the last problem. If you haven't seen it, it's the last video uploaded, except now we're using cylindrical polar coordinates. Okay, so again, it's going to start the same way. Our length that we're looking for will be the integral of this line element ds, and ds squared, so this is in cylindrical coordinates, will be d rho squared plus rho d theta squared plus dz squared. Okay, now they're calling rho just r, and r is a constant. So phi, you could think of that as being like dr, which is 0. And I'm going to replace this as just r d phi squared plus dz squared. So all I did here is I replaced rho is equal to capital R. Okay. So then I'm going to square both sides to find my ds. It's a square root of r d phi squared plus dz squared. Okay. So it mentions in the problem that phi is a function of z. So what that means is we want to factor out a dz from this, because when we do that, you'll probably be able to see here, but if I factor out a dz squared, I'll be left with 1 plus r d phi dz squared. And this is really phi prime as a function of z squared, which we wanted because of what they stated there. If they said z was a function of phi, then we would have factored out a phi, but that's not the case they gave us. So with that in mind, I'm going to go ahead and pull that out, and I'll have the square root of 1 plus r, and I'll rewrite this as phi prime of z. This is squared dz. So we have our ds here, and all we need to do is write the integral, and this can go from z1 to z2. So the integral from z1 to z2, the square root of 1 plus r, and then it'll be times phi prime of z squared dz. And that is, I'm sorry, this should be squared, this should be squared, this should be squared, because I just forgot to square it when I did this part. So that should be squared, that should be squared, that should be squared. But that is how you do this sort of problem.